Hello again. In this short video, we're going to talk about some important property called optimization, circuit optimization. But why? Why are we so concerned about optimization? Simple words, it makes your operation much faster and efficient. So in other words, when you talk about circuits which are implemented in most of our day-to-day electronics, like your cell phone, when you optimize a system, when you're talking about making it faster and making it smaller, and in other words, making it more efficient. So efficient, we're talking about these days, we talk about low power. But why low power? Low power is because you can have more battery life. Low power leads to better long battery, and even more importantly, not really hot. When we talk about circuits, they dissipate power by just charging and discharging circuits. When you talk about discharging a circuit, you dissipate the energy as heat. So the larger your circuit, higher the power consumption, the hotter the circuit it becomes. So as a digital designer, it's our job to make your circuit very, very optimal in terms of making it faster, smaller, and consume less power. So let's see here. Here we are given a logic function here, f equals wx plus so on and so forth. Here we have multiple product terms that are added together. For simplicity, I'm just going to take a look at two of them together. So, and now here, what I'm going to do is look into if there are any common variables to factor them out. Here we have wx, the first one, the second one we also have wx. So factor it out. That becomes 1 plus y, and in the third and the fourth we have w bar z. So factor that out. That becomes y plus y bar plus w bar x y z bar. Now here we know 1 plus y is 1, y plus y bar is 1, so that becomes wx times 1 plus w bar z times 1 plus w bar x y z bar. So that becomes f becomes wx plus w bar z plus w bar x y z bar. So this is your simplified function. We went from 1, 2, 3, 4, 5 terms to just 3 terms and reduce the number of literals as well. Now let's look at a different function. So here we have a function here, but h equals ab plus b bar c plus so on and so forth. But the point here is that we cannot combine these two together. There is nothing common right next to each other. So we have to do some rearranging. Look at on the function. We have ab here. Do we have any other product term with similar terms? We have a, b bar, d. So we're going to combine them together. ab plus ab d bar in one parenthesis. Now look at something else. b bar c. Do we have b bar c anywhere else? No. We're going to write it as is. Now with acd, do we have something similar? acd bar. We're going to look at acd plus acd bar. That is going to factor out as previously. ab 1 plus d bar plus b bar c. Here we have ac as common, so factor it out. That becomes d plus d bar. So here we have ab 1 plus anything, as we remember from our previous video, it is 1 plus b bar c plus ac times x plus x bar, or d plus d bar, becomes 1. So our function h is going to be ab plus b bar c plus ac here. So we reduced our circuit from 13 literals to just 6 literals. And one other point I want to say here is we have to observe that this is a product term, this is a product term, this is a product term here, and we are adding, in other words, summing all the products So we call this entire term as sum of product, or SOP, sum of products. Now, the last function we're going to look into in this video is something called the product of sums. Product of sum. So here we have, this is a product, this is a product, and this is a sum. My bad, my mistake. This is a sum term, sum term, sum term. We are multiplying them all together to make that a product of sum here. So first thing, this product of sum optimization takes a little more practice. So initially it is going to be a little challenging, but bear with me here. So here I'm going to rearrange this function and show you why in a minute. Basically, I swapped the second and third terms. I swapped the second and the third terms now. Now let's say in here, in the first two terms, I have z as common. So I'm going to temporarily write that as a and presume this whole thing as b, w plus x bar as b, this whole thing as c. So in other words, this becomes a function of b plus a times c plus a times w bar plus y plus c bar. Now we have a property which I'm going to share in the class, property 8b, which says a plus b times a plus c is going to be a plus bc. So in our terms here, this whole thing, this is a plus b and this is a plus c, that becomes a plus bc, w bar plus y plus c bar. So put a and b back. A is nothing but z and b is nothing but w plus x bar times c is x plus y times w bar plus y plus c bar, right? Now, there is one other property here. There is one other property, P14a, which I'm going to share in a minute. When we have a plus c times a bar plus b, that can also be written as ab plus a bar c. So what I'm saying here is, let's say if this is a, here we have z bar, which is a bar. So this whole thing is b, and this whole thing is c. We have a plus b times a bar. Let's say this is b and this is c. That becomes c here, a bar plus b. We can optimize this as ab plus a bar c. That becomes a is z, b is nothing but w bar plus y, plus a bar is c bar times c is w plus x bar times x plus y. And if you expand this even more, we have to apply this property again, P14a again. We have a function expands this to w bar z plus yz plus w x z bar plus x bar z. So here, this is one of our optimization here. So basically, we went from 9 literals to more. We went to 10 literals, but when we optimized, we made the circuit a little faster, which we will see when we design the logic circuits.